I'm Stacy, and today I'll be speaking about tools for collaborative machine learning. I've been a deep learning engineer at WiDS and WiDS for a few years, and I'll be focusing on specific features and visualizations from our developer platform. More personally, I can't decide whether AI safety or the climate crisis is a bigger existential risk for humanity. Maybe the latter feels more urgent these days, so I'll be sharing some relevant example projects which are open, public, and intended to be collaborative. As machine learning and data science practitioners, we have unique leverage in choosing where we focus our efforts, which datasets, problems, and applications we advance. And I believe that the more accessible, transparent, and collaborative the process of building and deploying models for these becomes, the safer and better the collective outcomes. So I want to show you how weights and biases, or W&B, can streamline workflows and facilitate collaboration on any machine learning project by connecting and tracking all the pieces of code, data, configuration, metrics, interactive analysis, insights, random notes, presentations, revisions, debugging, and all of that from everyone on the team. And beyond that, I want to encourage more of us to consider how our machine learning skills might help in environmental sustainability, AI safety, and other planetary scale challenges. When I've done an informal poll giving an earlier version of this talk, folks said that the hardest parts of working together on an open collaborative machine learning project were getting started, the setup of the existing code and the environment, followed by debugging, running into issues or regressions or getting stuck, and finally by coordination, or tracking and organizing next steps and who does what. Interestingly, in that poll no one voted for shipping, or making sure others can use your model or reproduce your results, which means either that part is very easy or very few people get to that point. A tool like weights and biases can help machine learning practitioners with all of these steps. So what is weights and biases? In case folks aren't familiar, it's a system of record. You can think of it as you would of Salesforce for a sales team or Jira for an engineering team to track and organize everything they do. Machine learning teams can use W&B as a lightweight and flexible developer toolset, and we're framework and infrastructure agnostic. So whether you're using PyTorch or Keras for TensorFlow or XGBoost, whether you're running locally on GCP or AWS, you can use weights and biases. Our tools are meant as a point solution for any step or use case in the life cycle of a machine learning project. This includes artifacts for versioning data in pipelines, tables for visualizing data interactively, experiments for tracking model development, sweeps for tuning hyperparameters, and reports for collaborative analysis and reproducibility. We also have CI/CD and production monitoring coming soon. And just to get really concrete, WANDB is a Python package that you can install with pip or conda. After you import it, it's a few lines of code to initialize a project. This is where all of your experiment runs will go. Then save any experiment configuration or settings like learning rate and epochs. Of course, defining and training your model, that part's still up to you, but you can log any metric like accuracy, loss, etc. You can also log rich media, audio, video, custom HTML, even interactive molecules. And all of that shows up in a beautiful interactive dashboard, which you can easily customize and share with your teammates. Now let's hop into some of the case studies. The first one is DroughtWatch, and this is a project done with Andrew Hobbs while he was at UC Davis. Now he's at USF. And the premise of DroughtWatch is that better drought monitoring can prevent hunger. Over the past few years, drought has been intensifying in certain regions, and as the climate crisis worsens, we can expect droughts to get more frequent, more severe, and affect more regions of the planet. In Kenya, a program has been active since 2011 to monitor drought conditions and provide financial support to affected folks in the region. This is called index-based livestock insurance, and it transfers resources to pastoralists or nomadic farmers, and they can use the money to cover household expenses. Let's hop into the first project. This is DroughtWatch, done with Andrew Hobbs while at UC Davis. Now he's at USF. And the premise of DroughtWatch is that better drought monitoring can prevent hunger. As the climate crisis worsens, droughts have been getting more severe, more frequent, and spreading throughout the world. This project started in Kenya, where a program has been active since 2011 to monitor drought conditions and help affected folks in the region. This is called index-based livestock insurance, and it transfers resources to pastoralists or nomadic farmers. They can use that money to cover their household expenses. The existing program uses a measure called Normalized Difference Vegetation Index, which is basically how green the ground cover is. As you can see here, in 2018, the conditions were much more green, much better than in 2019. While this is a great approach, it doesn't distinguish between edible and inedible plants. And so the idea of this project was, could we do better with deep learning and computer vision techniques? The International Livestock Research Institute, or ILRI, organized lots and lots of human experts, these nomadic farmers, to go to specific locations, take photos, and label them with a number from 0 to 3, indicating the number of cows they thought could forage in that area. These photos and labels are then correlated with satellite images taken at the same location using Landsat, resulting in over 100,000 labeled data points. Now we have a supervised learning problem where the goal is to train on these examples and predict forage quality directly from satellite images, which can be acquired much more cheaply in near real time. We've trained a few convolutional networks on this data. The benchmark launched in August 2019, had a big milestone at ICLR in 2020, and since then, 9 participants have logged over 2,500 runs and improved the baseline accuracy by 2%. Other folks are publishing papers on this data and using it to improve this work, and it's really exciting to see the community building on the existing benchmark dataset, code, and models to support and accelerate their research. In terms of next steps, of course, really deploying these models into reality requires continuing to partner with local organizations on the ground. We'd love to keep working to generalize and aggregate these results, build systems for other crops like cassava and rice, and transfer insights to other regions or ecosystems, or other agricultural metrics like yield, forage, pests, and so on. The weights and biases features that really support this project are, first of all, experiment tracking and media logging. Here you can see validation images in the browser as you're training these models, and metrics in real time, which lets you verify your approach and catch problems early. For example, some of these clouds might be a problem. Here I have a screenshot for the configuration of an experiment run I ran in August 12th of 2019, and I can see the exact git state and the command that I used to launch this experiment. So right now I can go into a terminal and type in these commands and have the exact same experiment restored with the same configuration of all the hyperparameters, which gets me much closer to reproducibility of my experiments. We can also see system metrics. You can think of this as the output of NVIDIA-SMI, and these are plotted in real time. You can see how much of the GPU I'm utilizing and time spent accessing memory, and it's all tracked automatically and very useful for debugging. You don't need to monitor anything separately. Finally, in the dashboard, you can see all of my experiment runs, all of their different hyperparameter values and output metrics, and I can filter, sort, group, and otherwise customize this dashboard and save my results to a collaboratively editable report. In terms of next steps on this project, there's hyperparameter tuning, data augmentation, architecture exploration. I'd love to show you a report on weights and biases, and this talks about DroughtWatch benchmark progress. You can see that you can include hyperlinks, rich text and media. Here's a chart of the validation accuracy for various submissions to the benchmark and more detail about them, and the validation accuracy over time, over the course of the benchmark. And what's really powerful is I can click into any of these submissions and see how other folks have approached the problem, see their charts, see their configuration, all of their settings, and so forth. And this is really useful for working together to solve a problem like this. And let's hop into Safe Life. This is a project with Carol Wainwright, a Wildlife Partnership on AI, and Peter Eckersley. Folks have probably heard of the incredible advances we've been seeing in deep reinforcement learning with games like AlphaGo and StarCraft, beating human-level players, and deployment of real-world robotic systems like Project Loon, which is stratospheric balloons that bring internet connectivity to rural areas and navigate using reinforcement learning. There's still many challenges remaining to deploying an RL system. It's tricky to set precise goals for these systems and to get them to adapt to change. For example, if a robot moves from pavement onto, say, dirt or grass, how does that affect its mobility? It's hard to build systems that explore safely as well. If certain explorations would cause a robot to go off cliffs, then it might never learn about those states. Learning from human preferences is also a challenge. How do we tell a cleaning robot to move our recycling, but not important papers we might have left on the floor? And finally, avoiding negative side effects is a challenge. How to do that generally, and that's the focus of this work. How do we tell our reinforcement learning agents to do precisely one thing and not do all of the other possible things that might occur? Progress in RL has been incremental, and there are no general solutions. Real-world systems still need lots of explicit constraints because there are loopholes like reward hacking. And here you can see an example where we have a boat racing around a level, and this agent discovers that it can get a higher score by going in a loop and getting all these target bonuses, right, instead of winning the game. You might say, oh, we need to formulate the reward more correctly to say that finishing this level is a requirement, but there are so many possible conditions and caveats which are hard to formulate mathematically. For example, if the task is to make a cup of coffee and nothing more, it's very hard to write out an explicit list to say, well, don't make the water too hot to drink, don't spill the coffee grounds everywhere, and so on. It's also very hard to evaluate the safety of these systems without proper benchmarks, especially comparing across agents. And this is the inspiration for Safe Life. This is a game environment where each level is procedurally generated and has some complex dynamics that try to simulate the real world. You'll notice 3 examples of tasks, one where the agent has to put markers in a certain blue goal state, one where the agent removes red markers, and one where the agent solves a maze. In all of these, the oscillating patterns are Conway's game of life. In each step, a cell lives if it has 2 or 3 live neighbors and dies otherwise. This creates many unique levels and simulates how an agent might explore in the real world. In all of these tasks, we want the agent to balance success, solving the level, with minimal side effects, which means not moving any of the other markers, not destroying any of these patterns, not creating too many, and so on. And of course, this is especially hard because we can't tell the agent explicitly to avoid the yellow dots or focus on the green dots, because that would be cheating. This is what the benchmark and leaderboard looks like. We have a section for human results because you can also play as a human. And the features that made this project much easier of weights and biases are, first of all, the workspace. Here I have sections for training, validation, and benchmark below. I can see live videos in this and really lay out my work. Sweeps have also been really helpful. And here's a screenshot of Carol's report using sweeps. You can hop into an interactive version in weights and biases and show you that we can also include LaTeX in reports. You can see the relationships between different hyperparameters in this chart and look at these beautiful correlations between reward and side effects when you set a different penalty. And what makes the task challenging in this trade-off between side effects and reward. If we increase the penalty too high, then the agent might never learn the task. If we set it too low, there will be lots of side effects. And a powerful aspect of sweeps and weights and biases is that you can write a configuration file, set a bunch of hyperparameter configurations, and then just launch your runs without needing to monitor them or try one combination at a time. And with sweeps, you can use grid search, random search, or Bayesian optimized search, and that will pick the next hyperparameter combination, and you can read more and try out examples from our docs. Here is my report on getting started with Safe Life. You can see embedded videos of agents. I talk about how to get started with the benchmark here and show some examples of runs. You can see the green prune tasks succeeding before the blue append tasks. And this is interactive, so I can also show the navigate tasks on the same sets of charts and compare in detail. And my readers can also see LaTeX and look at charts grouped by different variables. And this is really powerful for exploring. I'd also love to show you how tables, our latest feature for interactive data visualization and explorations, can help here. I have 40,000 rows in this table. Each row has a video and some of the metrics for that episode. And let's see if I can group by success. See some of the agents that succeeded. We only have 36 which succeeded. This is a short run. And I can see the distribution of other parameters. You'll see that the ones that didn't succeed all have length 50 because they stick at the same level for the whole time. And I can add columns here interactively to do something like look at the average reward. And I could even explore a penalty and set it here. You'll see that the average reward is higher for the ones that succeed. That's good. But I can interactively set and try different penalty functions in this table. When I'm done with a configuration I like, I can also export it to a report and share it with my teammates. And finally, the next steps for Safe Life are to tune hyperparameters, try different RL strategies. We currently have DQN and PPO, and we're very excited to explore multi-agent mode, learning from human feedback, and of course continuing to let the platform support any other safety challenges. And you can try it yourself. It's very easy, just a few cells in a collab. Next, I'd like to talk about Deepform, and this is a project with lots of collaborators. And the central goal here is to understand forms or structured documents like receipts or invoices. Here's an example of how this is useful in climate science. We have thousands of pages of historical weather observations, which are hard to extract. There are human rights archives that contain information about folks that would take years to pore through manually. This actually happened with a big financial investigation, which required 85 journalists over a year to compile all of the records. And this seems like a prime case for automation. And where we started with Deepform is looking at the 2020 election in the US and seeing if we could extract campaign financing data. And TV stations in the US are legally required to disclose political ads for campaign financing, but the trick is that this disclosure happens as hundreds and thousands of PDFs online. And all of those PDFs are in different formats. So one might look like this, with the advertiser here and the channel here and the total amount here, but then another form might look like this, and then another one might look like this. And so we wanted to build a general parser for any form, regardless of layout, starting with the 2020 election, building up to a proof of concept for these other fields I mentioned, and creating a public data set and benchmark. To get really concrete, the data preparation here, and I'm glossing over a bunch of effort, is to OCR all of the PDFs to produce the tokens and the geometry so that we know the bounding box of each piece of text, we know where it is on the page. And now let me hop into an interactive bounding box visualization in Weights and Biases. This is a report on the Deepform benchmark, and here you can see I've embedded some of the receipts, and the contract ID is highlighted in purple, the organization is in pink, the dates are in red, and I can interact with these and say increase the threshold for the confidence score. You'll see some boxes disappear as I increase this, and that lets me get really into the details of a particular document. I can also hide the predictions and just look at the ground truth and see how my model is doing on exact documents. Another feature of Weights and Biases that was really helpful for this project is projects. We had over 10 different projects with hundreds of runs, and the team was distributed during the pandemic, and this let us coordinate effort on different types of models, such as seek-to-seek or 1D convolutions. I want to show you one more application of tables. Here I used Spacy to extract named entities from these receipts that we saw just from the text. And I have made a table where individual extracted entities are logged with their type and the length of the token. And here I can do things like group by type to see which entity type is predicted more frequently. Looks like organizations and money. But let's look at the actual occurrences of these type of tokens. So how many of that type do we find? And I can run queries like this interactively without needing to write new scripts, write new cells in my notebook, or do anything like that. I can also look at, say, the average length of these tokens. Looks like money is most frequent, and maybe that's easy to distinguish by length from other tokens. It looks like it has 7 average length, and that's pretty short based on these. Work of art's probably not super relevant to our receipts, but you can see how this interactive exploration can really free me from having to rerun long scripts on my data. Here's a last view of 2 workspaces for this project. So on the left is mine and on the right is Jonathan's, where he's set up a much more detailed custom color gradient for our different runs and done a lot of parameter analysis. And there's lots of next steps on this project, especially comparing other state-of-the-art models and looking into how we can use semi or unsupervised learning on all of the data that we have. And finally, I want to encourage you to participate. The projects that I've talked about are benchmarks on weights and biases. They're useful for learning new skills, reproducibility, real-world impact, and distributed teams with shared goals. Of course, any project that you want to collaborate on doesn't have to be a benchmark, can be accelerated with weights and biases. And to participate, you can join or start a benchmark, share intermediate results more often, and grow our community at wanttobe.me/Slack. Finally, I'd love to hear from you if any of this is interesting, and thanks so much for listening.